Hello guys, we have seen the expressions for kinetic energy, potential energy and total energy of the particle performing oscillatory motion. What are these expressions? My kinetic energy is equal to half into k into a square minus x square. Then potential energy is half into k x square and total energy is half k into a square. Right, where k is equal to m omega square. Okay, m omega square. This omega is angular frequency of oscillation. Okay, now here if we have to look at kinetic energy, okay, as you go away from the mean position, that means as the value of x goes on increasing, correct, what happens to the kinetic energy? Goes on decreasing. Potential energy, when you go away from the mean position, your potential energy increases, but then total energy remains constant. Okay, that is what we have seen so far. We just added this expression and we got this. Correct. So total energy is going to remain constant. Now, how would the graphs of this kinetic energy and total energy look like? We will see that, but then before that, let us find what is the total energy at the extreme position or total energy at the mean position. So I'll just write down here, at mean position, x is equal to x is equal to 0, correct? So my kinetic energy would be equal to half k a square, correct? Half k a square. What about potential energy? Potential energy is going to be obviously equal to 0, correct? And total energy is equal to half into k into a square, right? At extreme position, my x is going to be equal to, amplitude, right? So it is going to be equal to a, and my kinetic energy would be equal to half into k into a square minus a square. So that is going to be equal to 0, correct? What about potential energy? It is going to be half into k into a square, and obviously total energy is sum of these two, that is half k a square. So the total energy remains conserved. It is conserved whether you are at mean position or you are at extreme position, the total energy will remain same. Now again, if you are at some other intermediate position, again over there you will get the total energy same as half k into a square. Now coming to the graph of how it would look like. Okay, if we have our displacement over here, okay, and energy over here, so let us plot energy against displacement. Now you must have seen here that at mean position my x is equal to 0. So if this is my x and I'm here, so that means this is my O, or I would say it is my mean position. At mean position, kinetic energy is equal to total energy. That means kinetic energy is maximum at the mean position, correct? So it would be somewhere here. Okay, let us say kinetic energy is maximum. Now what happens as I move away from the mean position, my kinetic energy goes on decreasing. Okay, so if I move on the positive side here, and maybe on this side would be, let's say, negative here, and my energy would go on decreasing here, correct? But then same thing happens when I go on the other side, correct? So my kinetic energy, when I go on this side, it is again going to fall. Okay. What about potential energy? At mean position, the potential energy is 0, but kinetic energy is max. So kinetic energy is maximum. So I just name this as Ke. Okay. And for potential energy, I'm going to use blue ink. Okay. Now, before plotting potential energy, I'll just make a few markings here. Okay. What is going to be the maximum potential energy? Is it not half Ka square? Correct? Half Ka square here. Right? So, and this is the level of half Ka square. So, I'll just mark it over here. Okay. So, that is the maximum. Okay. And this point, okay, this point is equal to my amplitude. Correct? So, this is amplitude. So, when I reach that maximum displacement from the mean position, that is the amplitude position, my potential energy will be equal to maximum half Ka square. So at mean position it is 0 here, and at extreme position on either side it is half Ka square. So my potential energy would vary like this here, and it will be from here it will be like this. Correct. Now you must have this thought might come to your mind, that why the graphs are like this. They look parabolic. Correct. They look parabolic because they are parabolic. And why are they parabolic? Because I have the expression half kx square here, potential energy half kx square, and kinetic energy half k into a square minus x square. What is a parabola? What is the general profile of a parabola? You have, I'll just briefly tell you what are the parabolic profiles. Okay, you can have 4 profiles, parabolic profiles of this type here. Your first one is like this, your second one is like this, third one is like this, and fourth one is like this. Now, what is the equation, general equation of this parabola? The general equation of this parabola is y square is equal to 4ax. This is y square is equal to 4ax, but minus of that. This is x square is equal to 4ay, and this is x square is equal to minus 4ay. Or then I would say 4ay is equal to minus x square, or then I will say y is equal to x square upon minus x square upon 4a. Correct. So this is what I'll have here. Okay. What about this? X square is equal to 4ay. I have x square here. Okay. I have my x on x is on my x axis, and on y axis I have energy here. Correct. So my E would be as good as y there, and my y is equal to half k into x square. So the graph of potential energy is this. It is like this parabola. Correct. What about kinetic energy? For kinetic energy, it is parabola of this type. Okay. It is inverted parabola. So I have my kinetic energy graph like that. Okay. And then this is the point of total energy or maximum energy over there. Correct. So that was about energy of particle performing oscillatory motion. Now let us see the total energy. It depends on a few things, few factors. What are these factors? Okay, I'll just clear this graph and things on this side, but I'll retain the left hand side here. Okay. Now see here, my total energy is half k into a square. And what is my k? My k is equal to m omega square. Right? So my total energy is equal to half k m omega. So in place of k, I am going to put m omega square. M omega square into a square. M is the mass, omega is the angular frequency, and A is the amplitude. But now what is my omega? Omega is 2 pi upon T, and my T is amplitude of T is my periodic time of SHM. Okay, or can I say 2 pi into F? F is the frequency of oscillation, correct? I'm going to substitute that here, so it will be half into M into 2 pi F square A square, correct? It will be half M 4 pi square F square A square. So this 2 and 2 here, so it would be 2 pi square into M F square A square. This is the total energy. Now here, if you can see, 2 is a constant and pi square is a constant, correct? So they are just numbers, okay? Then what I can say here is total energy is proportional to M F square A square. So that keeps us, therefore total energy is proportional to mass, it is proportional to square of frequency, it is proportional to square of amplitude. Total energy is proportional to mass, proportional to square of frequency, and proportional to square of amplitude. What does it mean? If you double the frequency, your total energy will become 4 times. If you double the amplitude, it becomes 4 times. If you double the mass, it will be 2 times. Correct? So that is how it is. If you half the frequency, it will become total energy it will become 1/4. If you half the amplitude, it becomes 1/4. Correct? So these are the things that you need to understand. In the next video, we are going to talk more about combination of SHMs. Thank you so much.